Welcome to BKW Physics. I'm Mr. McConnelly. We're going to do some demonstrations here. And before I tell you what they are, I'm going to have my students kind of fill you in on that. If I'm taking a laser, and by the way, if this laser does shine towards your eyes, just tell me it's all right to do it for a second. You don't want to stare at it, okay? You're not going to go blind instantly or anything. But if I shine the laser light like this, so it's hitting the table, it's bouncing off of that mirror, and it's probably going towards Kristen, right? Did you see it? No. Okay, it's going that direction. What am I talking about? What area of physics is this it's bouncing off? You said frac, and you said fled.
Reflection.
Reflection. Reflection. What makes it a reflection? Or what are the key characteristics with reflection? Of?
Incidence.
That's a good word, incidence. So the angle of incidence.
The same angle, so it equals over as it is on the other side.
Right, and what's the one called on the other side when it bounces out?
Angle of reflection.
Yeah, it is. It's just the angle of reflection. So incidence is the same as reflection. And Kristen said a really good thing in between two. You measure the angle from that dotted line in the middle, which is the normal. Okay, so it measures from the normal. All right, so then what is this one? If I take one of these and I'm shining it, and instead of it going straight, it's hitting Jane over here. So it should go right toward Bob, but it hits Jane. Why? Refraction. Okay, that's refraction. What's the key? Why? Okay, there's the key. You're getting a change in speed. How fast does this laser light normally travel?
38
units? You know that? Okay. So 3e8 meters per second. Now it goes into this material. I can't tell you really what the speed is at this moment, but we have a way to figure it out if we want to later. But at this moment, I can't tell you what the speed is in this block of plastic. But I do know that it must be changing speed. And the way I tried to show you the other day was, if you think of the laser light as traveling along like this, then what part hits first? This end. So what part slows down? That end. So it goes like this, it hits, and it bends it. The more dense this is, remember we talked about glasses? What did we learn about the glasses?
The angle that it reflects glass is different.
Right. And so if you have very poor eyesight, sometimes they can't even use the plastic lenses anymore. They have to step up to the glass ones because it has a higher, now what's the name of that thing? The reason it bends, what's the term that we used to mean that this is more dense than something else? What letter is it?
N.
N. What's the term?
It was
That's the end of it. It's three things.
It's
blank
like
of blank. No? Index
of
refraction.
Oh, my
Index of refraction. So there's different index or indices of refraction, and glass is a higher one. Now on your chart, in your reference table, we noted yesterday that the highest one we could find there was actually the diamond. And there'll be a whole problem where we talk about that, because when you look at a diamond ring, you're like, oh, it's so sparkly and lovely and it looks great. Well, there's a reason to use diamond. Because diamond actually traps that light inside because of the high end value. And I'll show you the problem and why it works, and I'll totally ruin the allure of why you get diamonds, because I'm like that. So, and rainbows, I ruined that already. So, the next one is, what if this one will probably turn off the lights for us. Do you mind doing that?
No.
Thank you. this little glass plate here, although it can't be seen on camera, and probably even the people standing close to me can't see, has lines that are really, really close together. And if they're really close together, you shine a light through, what physics principle is going to be demonstrated if the light can actually make it through the small one? Diffraction. So we've talked about reflection, refraction, diffraction. You don't say a diffraction, but I'm just trying to exaggerate. So diffraction. So if it goes through this small opening, you should get some sort of spreading out of the light. So what that looks like, I'll show you here. And it shines back in your eyes, Bob. Here, okay? Alright, you see it there? Look it right on the block. Cameraman, would you mind spinning towards that block? Oh, you're there already. You're so good. So, maybe I'll use the green one, see if it looks a little bit better. It's kind of dim with that purple. Try this one. Oh, that's... There it is. See, that laser beam is normally round. When I shine it through that narrow opening, look what it does. It makes little dots that are spread out horizontally. And if I turned it the other way, of course, it would spread those dots out vertically. And we talked about that experiment, Young's experiment. Remember how he set it up? He put one opening, he let the light go through, and then he put two other openings, and he got those dots. And that's the interference pattern. This is an exact demonstration of that. All right, so those are the three different things: reflection, refraction, diffraction. But what we really want to do today is we want to take this huge chunk of, it's not glass, it's plastic, so in case I drop it. It's all dirty though, it looks terrible. Alright, it's better. We want to take this chunk, and first of all, I'm going to demonstrate that the light is really going to be bent quite a bit as it goes through it. But to help you see it a little bit better, I'm going to put a white sheet of paper underneath it, and this way it'll just make it clearer. And if it's still not clear enough, we can close the window blinds too. Thanks for grabbing that for me the other day. Mr. Baker helped us out. So, hopefully here, you can always turn the power down all the way before you plug these in. You don't have the power turned up and then you touch it, it's like a spark or a surge, because that is never good for electrical devices. So you connect one to the positive, one to the negative. We're using DC, direct current. Okay, lovely. So, I don't know how much time we have with this thing working, like I said, because I don't know. But, if I take and shine the laser beams through like this, and I can move it so you can see. You're fine as long as you don't let it shine right in your eyes, okay? Okay. You can see that these go straight through. But, if I start going at an angle, and would you mind grabbing a meter stick? Because it'll help me line up something for you. You can probably see if you're at your vantage point that these lines don't line up with those lines, but it might not be clear to someone else. So I'm going to use the meter stick to show you quick. If you take these lines right here, see how they're coming out? That's straight. Then the one furthest over here should continue and end up there. Where is it? It's over here. So, here is your task. Here's your task. Oh yes. Oh yes. Get ready. You are going to create, develop a little experiment or a little way in order so that you can figure out what the end value is of this chunk of plastic. And you can use a lot of things. We can draw right on this paper. We can mark where the lasers are going in and out. But in the end, you've got to use information gathered from here. And you've got to tell me what the end value of this is. So let's start with, what do we know? What are the things we know as starting off? End value out here. 1. End value right here, 1 thing. Do we know anything else?
No.
Not really. Alright?
You can find it.
What can we find?
The angles.
Okay. So what would be a good method here? We're working as a group for a little while, then I'm going to break into smaller groups.
A protractor.
Yeah, let's grab a protractor. Can I borrow someone's pencil? Because I think we should draw it right on here. And I'm going to back up a little so we have a little more space. Thanks, I got two of them. Alright. So what am I doing? What am I doing? So I'm going to draw on here. What am I drawing? Coming in? Now, what do we want to do? Do we want to use the right one, the left one, the middle one? Does it matter? That would be perfect. I'll need that in a sec.
I don't think it matters, but you have to use the same line on the other side.
True. Yep. Does not matter. You got to use one. We got to pick one. So, what's your pick?
Closest to you.
Closest to me? Okay. So I'm going to put a little mark here where it left the device. And just because I'm afraid I might hit the device, I'm going to put a line around the device too. That way if I whack it with my hand or something, we don't have to start again. Then it's leaving here and it's hitting the glass right there. Can you mark for me where it is on the other side, please? Perfect. And notice he chose again. And let's put a mark out. Put it about that far out. Yep. Okay, good. Now, last thing I think we should do, again, just in case we bump something, I'm going to do this. That way we can always put the glass block. Pencil's not really working too well. Switch. Okay. Now at this point, I'm going to move this. I'm going to shut that thing off because we have all the information we need. So what I'm going to do right now is I'm going to break into some groups. We can stop filming for a bit. Your challenge, hold on, your challenge at home if you're looking at this through the video, did you stop already? Okay. The challenge at home is calculate the end value of this plastic block, given what we have here. And you're not going to have the specific numbers yet, but if you make up an angle here, and you make up an angle here, could you calculate the end value? That's your challenge at home. UKW Physics, Mr.